So now we're going to try our Bayesian methods on real data. In particular on the data from Eurostat that we gathered before. Yeah, so we start with importing the data. So we say data frame is from pandas read CSV. And if you save this in the same place as I did before, this was in the directory data, and then we have this file health data.csv, and then let's quickly describe what the data looks like. So let's run this. So we load the data, and you can see we have the variables that we looked at before. So we have preventable mortality, treatable mortality, GDP per capita. We have a year variable. We have for income, Y, quantile 1 all the way up to 5. We have body mass index, smoking, and binge drinking. Now, as you can see, at the count level, I have 446 preventable mortality and treatable mortality. I have slightly less GDP per capita. And then, for instance, my quantile variables are 378, BMI is 420, etc. Yeah? So I have different number of variables, counts, for different variables, which means that I have missing variables. Yeah? So in some rows, some of these variables do not have a value. So we have to deal with these missing values, and we're going to deal with that in two different ways. The first way is actually the incorrect way, but it's simple and it's what often people use. We're going to simply delete all rows with missing values. So that's going to imply that we're going to lose lots of observations. And then later on we're going to use the Bayesian way to deal with this, which is basically to model the missing observations. The second idea is that we're trying to understand mortality. And we know that mortality is a function of income. But we do not believe that if your income goes up by, let's say, 10 euro per year, that your mortality will go up as well. Yeah, the idea is more that there's an order of magnitude effect of income on mortality. So that's the way we're going to deal with that. So let's get rid of this space. So we're going to plot income against mortality, but we're going to do this on a log-log scale. Yeah, so this code is slightly complicated, so you don't need to understand everything that's happening here. Basically what I'm trying to do is to get, we have 24 different countries. So we need a color scheme that will actually help us distinguish these 24 countries. And we make an attempt here, so this is also stuff to do with the coloring scheme, trying to sort of stretch it so that we can distinguish 24 different countries. And the upshot is that actually we can't. So later on we're going to look at the way to make the same plot that we have here interactive, because then when we hover with our mouse over the different points, it will give us the name of the country. Yeah, so, but first we're going to use matplotlib. Later on we're going to use Altair for the interactive plot. So what we're going to do is we're going to have a figure with two subplots. So this means it's going to be one row, two columns. They're going to share the Y key, so this odd thing here means true. So we're going to be the same values on the y-axis and the same value on the x-axis, so that we can easily compare the two figures that we're going to plot. Then we're going to loop through the countries, and for each country we're going to plot both for women. So here we make the selection of the data frame female, here we make a selection male. We're going to plot GDP per capita on the horizontal axis, and we're going to have treatable mortality on the vertical axis. Our label is going to be country. Yeah, so country will simply go through this list, Belgium, Netherlands, whatever. Then the x's are going to be in such a way that we're going to set the y scale to log, and we're going to set the x scale to log. So it's going to be a log-log plot, which basically means that it's going to plot the order of magnitude of the effects. On the x label, we're going to have GDP per capita. So this is for the first plot, the one on the left. This is for the second plot, the one on the right. And the y label is going to be treatable mortality, because that's the thing that we're going to plot. So here we have treatable mortality, and we're going to do this for female and male. Yeah, so finally we have the legend command to make sure that it is actually plotted, and it's plotted outside of the pictures themselves. Yeah, so this is then the graph that we're getting. Yeah, so it's not so easy to distinguish the different countries that we have over here in these dots, so we're going to improve on that later on. The only thing I want you to observe now is actually two things. First of all, the fact that mortality for women, so for females, is actually lower than for males, but that the difference between the mortalities between male and female seems to is decreasing in GDP per capita. Yeah, so we have a difference. So when GDP per capita is low, male mortality seems to be a lot higher than female mortality. But as GDP per capita increases, actually the difference between male and female mortality is going to be relatively small. Yeah, so later on we're going to model that. We're going to have a dummy for female and male when we model mortality. But we're also going to have an interaction effect that this difference between male and female is reduced as GDP itself grows, GDP per capita. So that's the first thing to observe. There's a difference between male and female. The second thing to observe is that, when you want to sort of model this relationship, a linear relationship actually seems to be sort of, quite decent. Yeah, so we're going to have a linear relationship between GDP per capita and treatable mortality. Yeah, so that means we're going to have a relationship of this form. M is the log of mortality. Yeah, so capital M is mortality itself. Small m is log mortality. And we're going to model it as a line, basically. Yeah, so we have a constant, B0. And this constant will be different for females and males, as you can see. Yeah, it's going to be higher for males than for females. And then beta 1 is going to be negative because mortality is going to fall with income. And when you have a relationship like this between mortality and income, it basically means that this relationship between mortality and income is convex. And then when we use Jensen's inequality, we can see that, with a convex function, if you take two different values of y and you take the convex combination of these values, so the logarithm of y1 and the logarithm of y2, that's going to be bigger than when you take the logarithm of phi of y1 and 1 phi of y2. Yeah, so this is basically Jensen's inequality. And what it says is that, if I have a given expected income equal to phi y1 plus 1 minus phi y2, so in this case there is no income inequality, so both countries basically have the same income, then mortality is going to be lower than when I have one country which has income y1 and the other one which has income y2. Yeah, so if you believe that this relationship holds between countries as well as within countries, it basically means that income inequality will tend to increase mortality. Yeah, so we're going to model that formally. We're going to have we're going to introduce a variable income inequality into our data frame, which captures exactly this idea, that as income inequality goes up, the difference between these two values goes up. So the difference between the logarithm of phi times y1 plus 1 phi minus y2 and phi logarithm y1 plus 1 phi logarithm y2. This difference increases, so that's an increase in income inequality, and we expect that to have a positive effect on mortality, meaning mortality increases.